Good evening, ladies and gentlemen. We are ready to start, and it gives me great privilege to introduce Scott to you. Scott is a system architect with Leidos. Throughout his 40-year career with IBM, Lockheed Martin, and Leidos, he has specialized in the design, development of large, complex real-time systems. I worked with him on some of them, particularly in the domestic and international air traffic control applications. He has extensive experience in leadership, both as a technical, leader for overall requirements, overall architectures, and also he's a great person to be a mentor. And we have a young person here whose mentor is, right? He has been a chief engineer driving the team to a successful outcome, both domestically in the US and in England, and has supported a whole bunch of international traffic programs. He's here to talk to us about imagination as one of our most important system engineering tools. Scott Landro.
Thank you, Chandru. Thanks very much. I really appreciate the opportunity to come and talk to you tonight. When Chandru asked me to come and speak, it was probably March or April, and October seemed a long way away. And we spent the summer working on a proposal together, and wouldn't you know it, that October was here before we could blink. So anyway, I'm going to talk about imagination tonight as a very important system engineering tool. And I'm sure I'd be preaching to the choir here tonight if I said that the world gets more and more complex every day. And in particular, the problems that we try to apply engineered solutions to become more and more complex with every day. And as engineers and designers, we're asked all the time to use our imaginations to figure out how these complex systems are intended to work. We're given a set of requirements, we synthesize architectures and designs, and we do various forms of analysis, most of it on paper, most of it using our imaginations to figure out how the system is going to respond to its inputs and deliver the service that its users require. Of course, as the system complexity increases, that places an increased burden on us as designers and engineers. We're routinely asked to think through very complex scenarios involving lots of inputs, timing issues, failures, recovery, all kinds of unknowns and variables. And that really does require a substantial investment of imagination as we develop designs and engineer solutions. So I think that, in truth, it's really one of the most important tools that we have. So we routinely use our imaginations to imagine how the system is intended to work or how we intend the system to work. And, again, we're driven mostly by requirements, and, the regular cases are the easy ones. It's really what happens when the system steps outside of the green circle into an area where we're really challenged by a failure or by an unexpected input or by a timing problem. Those are the real interesting problems. And as much as we spend our time in the green circle, we really do need to spend time in the outer fringe here, thinking about what happens if this happens or that happens. And to me, that, I think, is really the more interesting and the more challenging part of the problem. Now, I've been working in safety-critical systems for a long time. We develop air traffic control solutions, and that's part of the fabric of what we deal with every day. But it may not be comfortable territory for everyone. So I'm going to talk tonight about a few systems that didn't work as designed. And I think I'm going to go through these cases one by one. I'm going to talk about the background and talk about the circumstances that caused each of these events. They're well-known events to most people here, I think. And there is a common thread, and that is that somewhere along the line, an engineer or a designer perhaps didn't apply as much imagination as they should have, and they missed a part of the problem in doing the design and engineering the solution. And that had terrific consequences in all of these cases. Some cases more than others, but we'll talk about that. I'm going to start with Titanic. This is probably a story that you're all familiar with. James Cameron did a film a few years ago that showed the events leading up to the 14th of April, 1912. And I should say this really was an important event for me, because when I was, I don't know, 12 or 13, my parents gave me a copy of Walter Lord's book, A Night to Remember. And I think I unwrapped that book and looked at it, and I said, oh, I don't know what this is. And I took a look at the back, and I was captivated right away. I think I sat down and read the book in one sitting. And I think now I have read just about every book ever written about the Titanic. And it still continues to fascinate me. This is a photo of the Titanic that was taken on Good Friday, which was the Friday before it sailed. It sailed on a Wednesday, the 10th of April, from Southampton in the UK. And you can imagine these maybe were the kinds of requirements that were written for that system. Safe and expeditious transportation of passengers on board from point of departure to point of arrival. The requirement to meet its service requirements for the entirety of the sailing season, which in those days was February through November. And another requirement which turned out to be fairly pivotal, and that is that this system was equipped with 16 lifeboats. Actually, it was equipped with 18 lifeboats, 16 regular lifeboats and 2 collapsibles that were stowed on top of the officers' quarters. But that was the number of lifeboats required by the British Board of Trade safety regulations. And that was given in a tabular form for ships of 10,000 tons displacement or larger. That's as far as the table went. 16 lifeboats was the requirement. And never mind the fact that the Titanic was 46,000 or slightly over 46,000 tons displacement. The growth in the North Atlantic trade had far outpaced the ability of the regulators to keep up with it. And as a result, Titanic was not equipped with sufficient lifeboats for all of the passengers. There was a gentleman, Alexander Carlisle, who worked for Harland and Wolff, who was the builder of the ship, who made a proposal that lifeboats ought to be doubled up on the boat deck. And the chairman of the White Star Line said, no, that would impinge on the wide promenades that our first-class passengers will want to use. And, you know, the ship is practically unsinkable. The things that we've done in engineering the integrity of the ship will obviate the need for extra lifeboats. That was quite a fateful decision. The Titanic was the second of 3 so-called superliners, and the 3 ships built for the White Star Line, Olympic, Titanic, and Britannic, were all built by Harland Wolff in Belfast in Ireland. They were delivered between May of 1911, that was the Olympic was first, and December of 1915, and they sailed back and forth between points on the continent of Europe and New York. It was a very, very lucrative passenger trade that had been growing for some time, and really continued to eclipse itself year after year. There was a pretty substantial first-class contingent of folks who spent their winters in Europe and summers in the US, and they were kind of the cream of society in the business world, banking world, politics. There continued to be a demand for passage from Europe to the New World, and as a result, there was a third-class trade that was economical, and the food and the lodgings were certainly adequate. And then in the middle was a second class for more or less normal, fairly well-off people. There was fierce competition, in particular between White Star and Cunard. And Cunard prided itself on having the fastest ships on the Atlantic. And White Star decided that it couldn't compete in terms of speed, that it would compete in terms of luxury. And these ships were considered the ultimate in luxury. I'm sure if you saw James Cameron's film, he very faithfully reproduced some of the fittings and the accommodation on the ship, and it is pretty amazing. One of the side effects of this, these superliners were larger than any ship that folks had previously worked with. The Titanic was just shy of 900 feet long. It was really a much bigger ship than captain or crew had ever worked with before. And that had some unforeseen ramifications. And in particular, in September of 1911, when Olympic was heading outbound from Southampton, it got into a situation where it was on a parallel track with a Royal Navy ship, the Hawk, and the Hawk made a maneuver to go behind the Olympic, and lo and behold, the Hawk just got sucked right into the wake of the Olympic, and there actually was a collision which damaged, the Hawk was badly damaged. The Olympic had some broken hull plates on the, I believe, the port side and the stern, and that was quite a big deal. There was, of course, lots of discussion of what had happened, and the accident was attributed more or less to the size of this liner compared to what people were used to, and the fact that there was suction associated with the wake. Well, that maybe was significant in the year following, when the Titanic had an encounter with an iceberg. So one of the things that I'll comment about the picture. The picture is actually a picture from February of 1912. The Olympic, which is shown on the left, had an event where it dropped a propeller blade, and it needed to go, since it was in service and the Titanic was not yet in service, they actually took the Titanic out of the fitting dry dock and they put Olympic in. They actually took parts from the Titanic to repair the Olympic so they could rush it back into passenger service. And one of the consequences of that was that Titanic's maiden voyage was delayed from the 20th of March to the 10th of April. And that, of course, was kind of a fateful event. In terms of design, Titanic was really well engineered, and there was a lot of thought given to safety features. The hull itself was divided into 16 watertight compartments, and they were laterally and longitudinally watertight, but they were not vertically watertight. Again, that had fateful consequences. The watertight bulkheads extended up to E-deck just a few feet above the waterline. And these watertight doors in the picture were of the type that was installed. Those doors could be closed either locally from below decks, or they could be closed on a signal from the bridge, electrical signal from the bridge. Titanic's outer hull was constructed in the traditional way using 1-inch thick steel plates with wrought iron through rivets that were basically pounded through holes in the plates, and the ship was riveted together in that fashion. One of the interesting discoveries, again, you know, there's been a lot of work done since the discovery of the wreck. One experiment that was done is they retrieved a sample of the metal plating from the hull, and they did some testing on it, particularly at extremely low temperatures. The sea temperature in the night of the accident was 29 degrees Fahrenheit. So they actually exposed that sample of the plating to that temperature, and they did some tests that are designed to test the ductility or the susceptibility to fracture. And that steel, because of the composition of the steel, tended to fracture a bit like china, a sharp, jagged fracture at cold temperatures, rather than a more flexible bending using the ductility of the material. And again, you know, here's another contributing factor. When the ship had an encounter with an iceberg, that cold steel didn't do very well. It didn't bend, it split, and that contributed to ultimately the loss of the ship. The chronology really starts as far back as 1903. There's some debate about this, but the story is that originally Lord Peary hosted some of the White Star officers for a dinner in London, and it was after dinner over cigars and port that the idea of 3 very large liners got discussed, and ultimately that led to the construction of these 3 ships. There's been some debate about exactly when that happened. The best reference that I found says it probably happened earlier than 1903, given the schedule for these kinds of things. That's the best projection. The Harland and Wolff order book has 2 ships listed, ship number 400, which was the Olympic, and ship number 401, which was the Titanic. The date of that is well known and it's documented. It's April 30th, 1907. So you can imagine that the first discussion of this whole concept may have easily been 1903 or earlier. The Titanic's keel was laid in March of 1909. The hull was launched on May 31st, and the hull then went into the fitting dry dock to have all of the internal fittings installed. The Titanic arrived in Southampton on the 3rd of April. It departed on a Wednesday. There was the so-called boat train that came down from London. People would get on board the train in Waterloo for a roughly a 90-minute train ride down to the pier side in Southampton. And traditionally, 12:30 was departure time. The White Star routes, generally, the ship went across the channel to Cherbourg in France, arriving there in the evening. And it then departed and went to Queenstown in Ireland. In this case, it arrived there at 11:30. And there is a series of well-known photographs that were taken by a gentleman by the name of Father Brown, who was aboard the ship in Southampton. He departed in Queenstown, and therefore his pictures have been made available because he didn't go down with the ship, including a very poignant photo, which is taken from the tender looking up, and there's Captain Smith looking down from along the side of the hull, last photograph ever of Captain Smith. So on its routine sailing schedule, it departed Queenstown on the 11th of April, and it encountered the iceberg at 11:40 on the 14th, and sank at 2:20 in the morning on the 15th of April. That is a photo of the Titanic as it's departing from Southampton. Quite a well-known photo. So regarding the Titanic's design flaw, I talked about the bulkheads, and the critical series of events really starts early on the day of the 14th. There were a number of ice warnings given to captain and crew and the owner, Bruce Ismay. There had been ships on the same track that were farther ahead of the Titanic that encountered a large set of pack ice. It was maybe farther south than was typical for that time of year, but it was well reported. There were at least, as I recall, 6 to 8 ice warnings that were given to captain and crew. And as far as anyone can tell, there was really nothing extraordinary that was done about that. They did post routine lookouts, and they were instructed to keep an eye out for ice. One problem was that the binoculars that they usually were equipped with were by mistake left in Southampton, so they were left only with their own eyesight to spot ice. At 11:40, temperature of the ocean is 29 degrees Fahrenheit. The ship has a glancing encounter with an iceberg. The ship passes just to the port of the iceberg. The iceberg kind of bumps along its starboard hull for about the first third of the ship, and the net result is a breach in the hull, estimated to be about 300 feet long. It compromises 6 of the 16 watertight compartments, and while the ship was designed to tolerate 3 and maybe 4, depending on which compartments there were, the net effect was to weight the front of the ship down, weight the bow down with a lot of water, and the bow sank far enough that the water level exceeded the vertical height of the watertight bulkheads. The water sloshed over to the next compartment, which added load, dragged the ship down, and this just continued. There were a number of eyewitness accounts who variously described the final events of the accident, and some people said the Titanic rose up and then settled back and slid beneath the waves. Some people said it rose up and broke in half. And so when Robert Ballard found the wreck in 1986 in 2 pieces, about 1,000 feet apart, that set that whole record straight. The ship did indeed break. The place where it broke is about 2/3 of the way back, and that was where there was a very large reciprocating engine on the lower decks, and therefore there were no intermediate decks, which meant that that was a weak spot in the hull. And ultimately, that's where the hull broke under the load of being suspended in the air. And this is a photograph from the 19th of April. Those passengers that managed to get into lifeboats were rescued by the Carpathia, another ship, and taken back to New York. The crew of the Carpathia also unloaded the lifeboats that they had hung on to, and there they are. So lots of things that weren't imagined in this particular case. A glancing encounter with an iceberg, a long breach of the hull that compromised multiple watertight compartments, and really, and this is kind of inexcusable, the fact that there weren't sufficient lifeboats on board for everyone who was on board the ship. I'm going to move on from water to air and talk a little bit about Apollo 13. Apollo 13 was Odyssey and Aquarius. Odyssey was the command module. Aquarius was the lunar excursion module. And you can imagine that these are the kind of requirements that maybe were written that described what it was in the original specification for this system. There are 3 components to this vehicle. There is the service module, which is that cylindrical component on the left. There is the conical command module. That's really where the 3 astronauts spend most of their time. Of course, the lunar excursion module, or LEM, on the right. And it has 2 stages, a descent stage and an ascent stage. And essentially, the service module on the left housed all of the oxygen, fuel cells, all of the sort of the infrastructure that kept life support available to the astronauts. The command module was really their habitat. There was an instrument panel and facilities for eating and drinking and surviving. Not a lot of room in the command module, but for this sort of 7 to 8 day mission, it was adequate. The LEM was really designed for a very short-term mission, descent to the surface, some limited time on the surface, ascent back to the command module. It would dock, they would transfer samples and crew back into the command module. The LEM would then be jettisoned. So it was really designed for a very short-term mission. So needless to say, the oxygen subsystem that provides essential life support is in the service module, and the design was based on redundant oxygen tanks. The electrical power for the space vehicle was generated by electrolysis. There were 3 fuel cells. There was also hydrogen and oxygen through electrolysis generated power for the vehicle, and also as a byproduct drinking water, which they used for drinking and cooking. The oxygen tanks were spherical, and they held oxygen at a supercooled temperature. And they did this probably because it makes for a more dense storage of the required oxygen. The oxygen tanks in that state tend to striate. You get kind of a frothy slush in them. And this has the effect of making the quantity measurements, when they measure quantity remaining in the tank, making those measurements inaccurate. So that tank was designed with a fan in it to stir up the slush to enable them to get more accurate quantity measurements. It also had a heater and a thermostat in the tank. The heater was designed to help them to vaporize the liquid oxygen and evacuate the tank after a ground test. They would typically fill the tanks up, fill the whole vehicle up, test it, and then when they were done, they wanted to evacuate it. And so they did this using a heater. And the thermostat was there to design or to prevent the tank from being overheated. Because the normal cryogenic state of the tank was 200 degrees Fahrenheit, minus 200 degrees Fahrenheit, the thermostat only went to 27 degrees C, which is about 80 degrees Fahrenheit. That, of course, had some ramifications. So one of the changes that was made at some point was they decided that normally the heater and the thermostat and all the equipment in the oxygen tank was powered with 28 volts DC that was available on the service module. But they made a design change to allow that oxygen tank to be powered either from 28 volts DC or 65 volt DC ground power, which was available in the launch complex. And so when they were doing ground tests and they wanted to evacuate that tank quickly, they could apply 65 volts and vaporize the oxygen and empty the tank out. Crucially, there was an electronic component that was not redesigned for the 65 volt ground power. And that ultimately led the very complex chain that led to this accident. The electrical system on board the ship consisted of the components below the dotted line. Those were housed in the service module, and components above the line, those were housed in the command module. There were 2 hydrogen tanks, 2 oxygen tanks, 3 fuel cells. The fuel cells could be independently switched between 2 buses, a service module bus A and a service module bus B. And as a byproduct, the fuel cells produced H2O. The 2 service module buses were fed through connectors to the command module, as was the water. And they, in turn, powered 2 main buses in the command module, a 28 volt DC bus A and bus B. And the thing that's significant here is that when they make their retro burn, they fire the service module engine to slow down just prior to reentry. They then jettison the service module. Well, they need to have power on the command module for the rest of the flight, from the time they jettison the service module until reentry is completed. And so the command module had to be independently powered, and they used batteries in the command module to do that. There were 3 batteries, one attached to bus A, one attached to bus B, and battery C, which could be switched back and forth. So you can see there was a lot of care given to redundant design, flexible design, and that ultimately proved to be the thing that saved this mission. Then from the 2 DC buses, they had inverters to power some equipment. They used DC power to power other equipment. And the equipment, essential equipment and non-essential equipment, was organized and distributed between the 2 main buses in a way that reduced the impact of any failure. So very complex design, very well thought out. And I think it's fair to say that the design work that was done on the human spaceflight program, you have to remember, this is the early 60s when this work was done. Really kind of advanced the state of the art when it comes to designing high availability systems, I think. So the story of the oxygen tank really begins with Apollo 10. Apollo 10 was Gene Cernan's flight, was flown just before Apollo 11. My wife and I watched the Gene Cernan documentary, Last Man on the Moon, because he was in fact the last man on the moon with Apollo 17. But he also flew Apollo 10, which did everything Apollo 11 did except land on the moon. They did all the maneuvers. They put a crew in the LEM. They flew the LEM. They descended to a certain altitude. I forget how far down they went. They came back up. It was really the dress rehearsal for Neil Armstrong's flight. The oxygen tank in question, and this was all painstakingly reconstructed after the event, was originally installed in Apollo 10, and they had to make some changes to Apollo 10, which required them to remove a shelf that was in the service module. And when they were doing that, they forgot to remove a retaining bolt, and as a result, the shelf slipped off a fitting that was holding it up, that had lifted it up, and the whole assembly fell 2 inches, bang. So now they thought, uh-oh, and they inspect the tank. They don't see any damage. And they, in the course of doing their retrofit on Apollo 10, they took that tank out of the vehicle and put the tank back on the shelf. We'll use it again a few flights down the line. But they never really inspected the tank. You can't look inside it. You can't really see what damage there may have been done. So the tank sat there on the shelf. Meanwhile, there were some changes to the specifications. They introduced this 65-volt DC requirement for ground power. And the supplier of the tank neglected to change the thermostat design. Crucial error, which ultimately was really the cause of the accident. So this tank gets installed on Apollo 13. Apollo 13 is on the pad. They fill it up with liquid oxygen, pressurize the whole system, running a ground test. Okay, test is over. Now they go to evacuate the tank. The tank won't evacuate. The first tank evacuates, this tank won't. They don't understand that. They talk to Jim Lovell, who signs off on a procedure that says, let's put 65 volts on the tank. They put 65 volts on the tank. They wait 2 days. The tank is not emptying. What? They could get oxygen into it just fine. They just couldn't get oxygen out of it. And they thought, well, oxygen going in is what we need. And, you know, on launch day, we're going to fill it up. And so we won't worry about this too much. Meanwhile, for 2 days, they had 65 volts applied to the thing. And actually what happened is the tank heated up to about 1,000 degrees Fahrenheit, because when they put 65 volts on the thermostat, it fused closed. And now they're heating the tank and heating the tank, trying to get the oxygen out of it. And the strip recorders the thermostat in the thing only registers up to 80 degrees because, the thing's mostly at minus 200. And so the strip recorder says 80 degrees is as hot as it got. Well, it got a lot hotter than that. And in fact, what happened is it essentially burned through all the Teflon insulation connecting the power supply to the fan motor. And on launch day, they filled the tank up with oxygen, and now they have a ticking time bomb. Apollo 13 gets launched. It was launched on can't see the date here, in April. The 11th of April. That's kind of uncanny, isn't it? April's a bad month. It gets launched at, I think, in the afternoon of April 11th. It goes 2 days and a few hours, and of course, everybody knows the story. They had just finished a live telecast back to Earth. 6 minutes later, they asked Jack Swigert to do a cryo stir, to stir up the tanks so they can get an oxygen quantity measurement. And he flips the switch, and about 2 minutes goes by, and bang. Jim Lovell eventually gets on the radio, and the famous words that everybody knows. Houston initially believes that they have an instrumentation problem. And there's a very interesting YouTube tape, which has got Capcom on one channel on the right, and it's got Gene Kranz. If any of you saw Apollo 13, he's the guy with the white vest. Really a no-nonsense, amazing guy who knew everything about the vehicle, knew all about his team and how to manage his team effectively, how to get them to give him input that he needed, and how to get them to do the things that they needed to do to allow the mission to succeed. And so they're connecting the fuel cells back and forth between bus A and bus B, trying all different things, trying to figure out what's good and what's not good. And on this tape, you can hear them going through this whole procedure. And they're trying to figure out, is it instrumentation or is there really a problem on the vehicle? Eventually, Lovell gets on the radio and says, tank 2, oxygen tank 2 now reads quantity 0. And we're having a problem with low voltage on bus B. And that was really the first sign that there was something serious going on. He then goes on to say, hey, we're venting something into space. I can't tell what it is. And Gene Kranz kind of puts 2 and 2 together and says, this is not instrumentation. A loud bang, quantity 0, venting a gas. We have a serious problem here. So over the next 130 minutes, oxygen tank 1 goes to quantity 0. So now there is no oxygen in the service module. So there is no electricity in the service module. And they're on batteries. Those batteries that I showed you in the picture that are really reserved for reentry. You got to have computers running during reentry because there's a very delicate maneuver that you need to make to get back to Earth safely. So fuel cells eventually shut down. They're on batteries, and they realize we need to power down the command module because we've got to save our batteries for reentry. So that's what they do. They shut down the command module in its entirety, and they power up the LEM. Remember I said designed for a day or so. They power up the LEM in lifeboat mode. They're going to keep the crew alive for the next 3 or 4 days. This is a photo that was taken after the service module is jettisoned, and you can see that the explosion basically blew a panel off the side of the thing, and the guts of the service module are all hanging out. It's a little bit hard to see, but that's quite significant damage. Ultimately, this is how it ended on the 17th of April. And, all the stories about the CO2 scrubber and the round cartridges in the square holes and all that stuff, which you've seen from the film. The next item is Challenger. And again, imagining the kind of requirements, the orbiter vehicle has 3 main engines. The external tank supplies fuel and oxidizer. It's hydrogen and oxygen to the orbiter vehicle main engines. Solid rocket boosters, they are attached to the 2 two sides of the external tank, and they are what give the vehicle sufficient thrust to achieve orbital insertion. Each of the solid rocket boosters was manufactured in segments, and those were mated together to form the completed booster. The mating segments were designed to maintain physical and mechanical integrity of the joint between the mated sections during launch and flight operations. And the system shall be designed to support launch and flight operations across the normal range of environmental temperatures encountered during launch and ascent. The SRBs were qualified to 40 degrees Fahrenheit. And as we shall see, the temperature on the pad that morning was 30. And overnight it had been 18 degrees. So Challenger itself, someone has said with over 1 million moving parts, it's probably the most complicated piece of machinery ever built. Originally, Challenger was built as a structural test article. It was designed to go through a shake test at Lockheed's facility on the West Coast. And that contract was led in 1972. They started assembly in 75, and the test vehicle was complete in 78 and went for its shake test. However, as is typical of the space program, they decided to repurpose Structural Test Article 99, and it became Orbital Vehicle 99. They basically took it back into the plant and retrofitted it with the necessary systems to enable it to actually fly missions. That contract was awarded in 79. They started at the beginning of 79 and was completed in 81. It was delivered to NASA in 82. They did a readiness firing in late 82, and it flew for the first time in April of 83. STS-51L, which was the final Challenger flight, actually flew on the 28th of January 1986. That was its 9th mission. The solid rocket booster design, the two mating sections were joined in a fairly complex tongue and groove kind of fitting. And once those sections were mated, there were pins that were inserted to connect them together. Again, it's the through rivet story, right? So just a variation on a theme. But a critical component of the joint was a pair of O-rings which went all the way around. I mean, it's a pretty hefty, I think it's 38 feet in circumference or something like that. Those two O-rings were designed to close or maintain the integrity of that joint, because when the vehicle ignited, the metal casing actually flexed such that the two parts pulled apart. And those O-rings were there to ensure the integrity of that seal. And they used zinc chromate putty to fill in the gaps and basically seal that up. But that was the original design that was in place when Challenger flew. In fact, there was evidence of problems with that O-ring as early as the second shuttle flight. And after the 84 launch of 41D, the test showed the first example of hot gas from the inside of the rocket booster actually blowing by the primary O-ring and beginning to erode the secondary O-ring. So there was plenty of data available to suggest that this was a real problem. And this was a criticality 1, I believe is the designation. The solid rocket boosters were a criticality 1 subsystem of the shuttle. And in fact, Morton Thiokol was in the process of redesigning this at the time of the Challenger accident. Originally, the launch was scheduled for the 22nd of January. And over the next few days, I think there were scrubs almost daily. They tried to launch 3 or 4 times. They finally replanned the launch for the 28th. And it was a very high-profile launch, right? It had, it was the teacher in space program, Krista McAuliffe, was one of the designated crew. So it was a very, very visible event, of course. The launch temperatures were predicted to be very cold. They predicted 30 degrees on the morning and as cold as 18 degrees overnight. On the 27th, there was an evening phone call with Morton Thiokol, and the subject of the O-rings came up. There was a lot of discussion. There was a contingent of Thiokol engineers who said there is no way we should be launching. We are not certified in the temperature range that's predicted for tomorrow. And a lot of back and forth. Obviously, politics was part of the equation. And ultimately, what's been documented is that everybody agreed they could go ahead and launch. On the morning, there was a significant amount of ice on the launch structure, so they held the countdown for an hour to permit some of that ice to melt. The risk was the ice would be shaken off during launch and damage the tiles, but ultimately they waited an hour. The vehicle was launched at 11:38. And this is actually a photograph that was taken while the vehicle was still on the pad. And you can see here, I've circled it, a telltale smudge of black smoke escaping from the very joint that ultimately failed. Vehicle flew for 73 seconds. And here's quite a remarkable photo that was taken probably, my guess is about 68 seconds. And you can see there's a plume of hot gas coming out of the aft starboard joint. Ultimately, that led to failure of the external tank and the vehicle exploded. The final case I want to talk about is Fukushima Daiichi. Daiichi means, in Japanese, the first. And there actually is a Fukushima the second, about 12 kilometers south of Fukushima Daiichi. Japan has a very interesting electrical system. The system is partially 60 hertz, partially 50 hertz, and there are some frequency conversion bridges in the middle. If you look closely at the map, you can see Fukushima Daiichi, you can see Tokyo, and Fukushima Daiichi is positioned right on the coast in a kind of an agricultural area on the coast of Japan. Literally, that site is right on the ocean. You'll see in a picture that I have in a moment. The little target that I've shown there is approximately the epicenter of the Tohoku earthquake, which was, my Richter numbers, I've heard 8 point something, I've heard 9, quite a substantial earthquake. So the facility at Daiichi consisted of 6 boiling water reactors, and they supplied 50 hertz since that facility was in the 50 hertz part of the Japanese system. Each boiling water reactor was equipped with cooling pumps to circulate cooling water. It was also equipped with emergency diesel generators to power the cooling pumps in the event that 50 hertz power wasn't available. Additionally, the site was equipped with DC batteries to continue operating the pumps in the event that both the commercial power and the generators were unavailable. But that battery backup was of a limited duration. Another contributing factor was that a number of the internal components in the reactor vessel itself were made from something called zirc alloy, which is an alloy of zirconium. And that metal is perfectly inert at normal temperatures, but under high temperature, it tends to produce hydrogen gas. And the reason zirc alloy was used, it was used for cladding on the fuel rods and also other metal parts in the reactor core itself, is that it has a very low absorption of neutrons, and in a nuclear reactor, the neutrons are actually what causes the fission. And what you don't want is a bunch of parts in the design that are sucking up the neutrons and preventing the reactor from doing its job. And those zirc alloy components actually contributed to the problem in this case, unfortunately. The design for the boiling water reactors was done in the 1960s. The design was originally done by GE. The reactor was manufactured by both Toshiba and Hitachi, and in this particular case, the reactors, there were 6 reactors on the site, were operated by the Tokyo Electric Power Company, TEPCO. The main components consist of the reactor pressure vessel, and that holds the fuel and control rods. There's an outer, approximately 2 meter, in some places thicker than that, 2 meter thick concrete primary containment, dry well, and there is a torus suppression wet well. You can see the torus at the bottom. Basically, that's a kind of an overflow and provides extra cooling capacity. Each of units 1 through 5 were equipped with 2 emergency diesel generators. Unfortunately, they were installed in the basement of the turbine building, as were all of the electrical interconnect panels. There were 125-volt DC emergency station batteries, providing about an 8-hour emergency backup. The facility, being perched right on the edge of the coast, was surrounded by a 5.7 meter seawall to mitigate the effect of waves. The ground level for the site was about, depending on what your reference point is, between 4 and 10 meters above sea level. I won't go through all the detail in this diagram. Suffice to say that the normal path for reactor operation and electricity generation is shown in the upper right. There's a steam line which comes from the reactor vessel, which feeds the turbine and turns the generator. The steam is then condensed, and there's seawater piping used to condense the steam, and then through some various condensate pumps that is returned to the reactor vessel. That's the primary loop for power generation. All of the other components here, I won't go through them in detail, are focused on keeping the reactor core cool. And there are several levels. There's a residual heat removal system, low and high pressure sprays. In units 2 and 3, there was a reactor core isolation cooling equipment. And in unit 1, there was an isolation condenser. It was further down here at the lower right-hand corner, the capability to inject water from an external source, in this case, the fire engine. So the electrical system, as I mentioned, was 3-way redundant. Normally, this was powered by mains power, but there were the electrical diesel generators as a backup and site batteries as a backup to that. This is a photograph of the site before the accident. You can see the 4 reactor buildings, right to left, 1, 2, 3, 4. The buildings in front of those, between the seawater and the reactor buildings, those are the turbine and emergency generator buildings. And the emergency generators were in the basement of that building. At the time of the accident, units 1, 2, and 3 were operating. Unit 4, and there are 2 additional reactors not shown, but off to the right, were not operating. Unit 4 became a problem on day 5 because its spent reactor pool began heating up because of the capability of keeping that reactor pool cool had been wiped out by the events that happened here. Really, the problems that occurred here at Fukushima materialized in a matter of hours. In the first day or 2, they were in trouble right away. And I remember watching this. We watched this on television unfold, and it was really scary. And I was pretty convinced that it was a lot worse than we were actually being told. And that turned out to be right. Not that I'm an expert on this, but I just was pretty convinced that they were in serious trouble. This accident was rated 7 on the international scale. 7 is the top number. Chernobyl was a 7. 3 Mile Island was a 5. 12 kilometers down the coast in Fukushima 2, they had 3 or 4 reactors, I can't remember how many. They also lost power, except they had one high voltage line coming onto the site. They were able to maintain cooling. They had some issues. They had some difficulties in getting those reactors shut down, but they did manage to get them shut down into a cold state within 3 or 4 days. And that event was rated a 3 on the scale because they did have some issues there. The net result of this is that there's a terrible, terrible cleanup and containment operation that's been going since literally the day that this occurred in 2011. It's still going on. There are now hundreds and hundreds and hundreds of tons of contaminated water stored on site with no clear plan as to what they're going to do with them. The cost, every time they estimate the cost to clean up and mitigate and repair and pay liabilities, the number keeps going up. I've seen 3 or 4 estimates. Every one is much bigger than the previous one. And, I suspect this will be at least 50 years or longer to remedy this whole problem. And in some cases, they don't really know what technology is needed to clean this up. So the critical events really were the earthquake occurred at 2:46 in the afternoon, Japan time, about 180 kilometers away. The reactors were designed to, with G-force sensors that would detect abnormal G-forces both vertically and laterally, and in the event that they exceeded a limit, would shut the reactors down through a process known as scramming. Basically, the control rods get inserted into the core, and the core begins powering down. So that all happened as expected. The G-force triggers were exceeded, and the control rods were inserted. However, the reactors don't cool instantly. They continue generating heat at about 1.5% of their rated capacity. So a pretty significant amount of heat is being generated. About 50 minutes after the earthquake, a 13-meter, 43-foot tsunami overtakes the plant. The 5.7-meter seawall was of little help in this particular case. And it basically flooded the turbine rooms along with the emergency backup diesels. They had turned on within minutes of the accident. They were running, but when the seawater overtook those buildings and flooded them, they basically couldn't operate anymore. And some of them were permanently damaged. Also, the interconnection panels were completely shorted out due to seawater. The reactor cooling system switched over to the DC backup, and they had about an 8-hour capacity, but flooding or grounding of the terminals basically rendered them unavailable. And literally within hours, reactor cores 1 and 3 boiled dry and began overheating. One thing that happened is the control room lost all power, so they had no way of even monitoring what was going on. They were operating in complete darkness with no instrumentation. And eventually, the Zirc alloy components in the reactor core began reacting with high temperature and, in particular, high pressure steam. And a very large volume of hydrogen was produced, and that ultimately led to explosions within the reactor buildings. These were broadcast on television. I'm sure many of you saw them. That's one of the reactors there. You can see that yellow structure is literally the top of the containment. It's been exposed to the elements. The little map on the right basically shows the level of exposure to radiation. Now, there are many different, I know of at least 3 scales for radiation. I think the typical annual source, a safe limit is 300 millirems a year. And I did the math here. If you were in the green region on the map, which is not trivial, that inner ring around Fukushima is 20 kilometers, so that's a pretty significant area. If you were in that area, you would exceed the safe limit in anywhere from 15 to 50 days. So that prompted a a series of evacuations, and basically that area was emptied out in a matter of days. I think a lot of it remains off limits. There was very productive agricultural land in that area of Japan that basically is unusable and will remain so for a long time to come. So this was a very, very significant accident. So as I said at the outset, really, imagination is important in all these cases. You can see, in hindsight, you can see things that people could have readily imagined and thought more carefully about. And these days we use systematic disciplines to help us, but ultimately there's an engineer or a designer thinking about what should happen, what has to happen, what the consequences that are, what do we do about it, making those decisions and making those trades, and mitigating the things that could go wrong. Again, we're talking about, this is pure imagination here. Those of us that work daily with safety critical systems, we're asked to do this all the time. And I know in the air traffic world, this is a very, very tightly integrated with even the basic design work we do, thinking about what happens on a failure, what happens on a switchover, what happens on error recovery. How do we make sure that all the messages got processed? How do we make sure incorrect clearances don't get issued, or incorrect data gets presented to controllers who then make decisions based on that data and clear aircraft to do certain things. So, but that behavior needn't be limited to safety critical situations. And the key question for me is, when is more thought warranted? So I did a little back of the envelope analysis here. This is my view. I think there's plenty of room to debate the numbers and the facts, the judgment here. But ultimately, the Titanic was about a $278 million loss when you think about loss of the ship, loss of service, loss of cargo. And that, I took the numbers from 1912 and converted them to 2015 dollars by using various inflation factors. There were 1,500 lives lost. I can't put a value on a life, so I can't convert that to dollars. I wouldn't even try. Other impacts, I don't think there were other impacts beyond that. The bottom line here is that design limitations of the whole design and an inadequate supply of lifeboats created an opportunity. And the accident occurred probably because the standard conduct of the day was to not pay a lot of attention to ice, and we just sail for the convenience of our passengers. And I think in the inquiry, they established that that sort of behavior was common practice. That doesn't make it right, but that was the common practice of the day. And one of the outcomes was that was the regulations and practices were modified. So, the case for further effort, I think, my assessment is, yeah, there is a case for further effort, particularly when mitigating the lifeboat problem is so easy. I mean, that seems tragic to me. Apollo 13, my assessment there is that there was an awful lot of attention given to careful and prudent design of the systems, and that enabled an improvised response to the accident, which ultimately led to the successful recovery of the crew. There were no lives lost. We didn't lose the vehicle any more than we would have. The service module gets jettisoned, the LEM gets jettisoned, the command module comes back to Earth, and it did in this case. But what they did lose is the mission. And I claimed we learned a lot from the mission as it unfolded anyway. So I kind of derated the cost of the mission and said, well, we really lost maybe half of the mission cost. It's, over $1 billion ultimately. Challenger, we lost the vehicle, we lost the mission, and In total, you know, over $3.5 billion. There were 7 lives lost. To me, this case is a case where the risk of a problem happening was very well known. And, you know, I think the cost of doing something notwithstanding, the fact that the risk was known and nothing was done about it, to me is tragic. I think the commission that investigated the accident concluded that there was some significant erosion of the national safety culture, and they had done this in the past. They'd gotten away with it. We'll do it again, and we'll get away with it again. And you know, that was a slippery slope, I think. I think also the defects with the O-ring joint were known. That problem was being re-engineered, but that response was very slow in coming. You know, on a big program, it takes a lot of energy to turn the ship in a new direction, and I think Morton Thiokol was not moving out smartly on that. Even though they had serious concerns, they were not moving with urgency to resolve that problem. So I think that's to me, we should have spent more energy on that. In the case of Fukushima, I think the thing that dominates here is the cost of an accident. And, you know, I think my numbers are low, and they're pushing $100 billion. And we don't yet know what the impact is going to be in lives. Certainly we would expect cancer rates to increase, although no deaths have been directly attributed to radiation problems. I think there's likely to be something that emerges from that. I think the long-term impact on the environment, the loss of the agricultural resource for Japan that doesn't really have a lot of resources to begin with, I think that's huge. And that environmental impact is not limited to Japan. There's evidence that the radiation is spreading through the Pacific and into the ecosystem and having other unintended or undesirable impacts. The thing that is amazing to me is that Japan is prone to earthquakes and tsunamis. I took a look today. Japan has had 29 earthquakes of magnitude 7 or higher since the year 2000. That's like 1.5 a year. And the fact that the Nuclear Regulatory Commission, as far back as 2000, said one of the most serious risks for nuclear operators is the risk, well, in the case of Japan, it's the risk of a seismic event causing a loss of cooling, and there was nothing done about that. And you know, to me, that's really a shame. And now they're dealing with the ramification of that lack of imagination. I could not help but include these pictures. These are tsunami stones. They're sprinkled all through Japan. And they've been there for quite a while. And they basically record where the tsunamis came to in the past. Many of them really date from the late 1800s, where there was a huge tsunami that had a major impact. But nonetheless, they're put there to remind people of the danger of tsunamis. And I don't know where the tsunami stones are in Fukushima, but you know, this is not something that people are unaware of. So I couldn't help but I went to the INCOSE site and I found this definition of systems engineering, and I highlighted some of the words. Enable the realization of successful systems, considering the complete problem. And that's where our imaginations enable us. Thank you very much. I have one more thing to show you. You saw this picture on the left. It's the Titanic leaving. This is a picture that I took in Southampton in 1998. My wife and I were on assignment in the south of England, and one day, shortly after We actually saw the Titanic film in Southampton, barely a mile from where the Titanic left. One Sunday, we decided we were going to drive over to the port. And we spoke to the security guard who said, nah, there's really nothing here. But I knew better. So we drove onto the port. We drove down to the quay and got out of the car, and we're standing there looking. Here comes the security guard in his vehicle. And he says, now, sir, you're not allowed down here. I told you that there was nothing here to see. And you're not allowed in this area. It's dangerous. Normally, we'd call the police and escort you off the port. Oh, so, all right, you'll have to get back in your car, sir, and follow me off the premises. So we get back in the car. We drive back out to the security gate. And he comes to the window and he says, are you visiting? I said, no, I live here. You're from America? Yes. And I'm very interested in the Titanic. I've read all the books. And he says, just a minute. Follow me. And he gets back in his car. He takes us right back to where we were. And he gives us a guided tour of here's where the boat train came in, and here's where the ocean terminal was. And he picks up a railroad spike and says, here, have a souvenir. And so that was my picture. You can see the bollards there from the original picture and from my picture. So I got to stand right on the place where Titanic left from. So that is it. Thank you very much.
Any questions?
Questions? Yes, of course.
In the movie, the Titanic, I wonder how the movie was implied that
Historical detail in the Titanic movie was they implied very strongly that they were trying to set an Atlantic crossing speed record. So they were running it at pretty high speed. Is that true?
I don't think that's true. I think that Cunard had the Atlantic crossing record at the time, and it was faster by a large margin than the White Star liners could achieve. The part of the market that the White Star went for was the luxury part of the market. The appointments, the paneling, the decorating, the architect, the decor was all, done to the max. And that part of the film is very accurate. In 1911, there was an edition of Shipbuilder magazine that featured the Titanic, and there was a great collection of photos that were taken on board the ship. So there is a wealth of authentic evidence to describe the appointments on the ship, and all of that was faithfully reproduced in the film. That part, I think, is very accurate. I think the speed record thing was done really just to ratchet up the suspense level in the film, and I don't think that there is anything to that.
One of your presentation leads me to ask the question of what do we need to do to change the education of engineers and systems engineers so that they have the mindset to think beyond a narrow set of needs, or how do we get them so that they think the way you, based on what you've learned, how they should change their modus operandi for engineering?
Well, I think that's a critical question, and I suppose I would say I'm not a particular expert on any of these. Maybe the closest I would come to is the Titanic, just because I've read a lot about it. But I have a curious mind, and I think that every failure is a learning opportunity, and really that's, I think, the key. That anytime we fail, we have to take the time to learn what we did wrong and what we're going to do differently next time. And that's an essential step, I think. Yes?
I have a question. Yeah.
It appears the Titanic appears to have 4 acts. In fact, only 3 of them work,
That's right.
and the 4th one was there for appearances.
It was.
And that was, to me, that shows a fundamental lack of engineering discipline.
That was a bit of marketing. And the fourth stack was added because the Cunard liners had 4 funnels. And even though the Titanic's design required only 3, they put a 4th one on there. The aft funnel did nothing. It was there just for decoration. But really, to keep up with the Cunarders, 4 funnels, we can't have 3, we need 4. So that's why that happened. That was a very conscious bit of marketing that the White Star Line went for. Yes.
Yes, I wanted to talk about the Challenger-esque question. I lost a friend, El Onizuka, on that mission.
Oh, wow.
And so I've had some, the opportunity to look into some of the facts and
Yeah.
opinions surrounding it. And my impression that I took away, and it's been a few years, of course, was that Morton Thiokol engineers really knew what the risks were. They were trying to do the right thing. But you mentioned an important thing a while back, and that was politics.
Yes.
I think it was more of a political, this is just my impression, political malfunction than it was an engineering malfunction. Now, I'm sure you're familiar with Dr. Tufte and his
Yes.
discussion, and he has a
Absolutely.
famous PowerPoint
Yes.
from the briefing given by Thiokol or given
Yes.
to be given. And if that's accurate, then that's the smoking gun, I think, that everybody should look at.
I think you're right. There is
yeah.
there was a set of data presented by Thiokol. There were people that were absolutely convinced that there was going to be a problem, and they were very passionate about voicing their concerns. There was a set of data presented in a meeting. I think what Tufte determined was that it was a particularly bad presentation of the data, and it was we've all heard death by PowerPoint. I think he criticized the presentation of the data, and it didn't really make clear the nature and significance of the issue. And it, ultimately it was not convincing enough to delay the launch.
Yes, that's true. And if I remember correctly as well, he was more concerned at the time I heard him speak about it with the duplicity of the PowerPoint and how the PowerPoint was able to manipulate
Right.
a lack of facts into a decision that wasn't supported.
Yeah. Yeah, I know the principal Morton Thiokol engineer, he passed away not long ago, and there was an interview before he passed away. And, he expressed great regret over not having been more persuasive in making his argument. But
the Richard Feynman
Yep.
Minority report that was in the report and some of the literature regarding that since said that there was an inflation in the probability of success
Right.
that might have been as much as a factor of 100 going up the Morton Thiokol chain of command.
Yep.
And that in and of itself is indicative of the strength of the politics.
I think that's absolutely correct. I know that I believe it's true that that I don't know whether there was a State of the Union the very night of the accident. I think maybe there was, and there was a lot of pressure for a successful launch so that Ronald Reagan could make some statement about the successful launch in the Teacher in Space program. And I have no doubt, and I think anybody who's studied it has no doubt that there was politics involved in the decision to launch. So
There are no more questions. Thank you very much, Scott.
we're good. Thanks.
Really appreciate it. And God, where do you go? You always raffle out.